What we're going to do today is we're going to look at the functional groups of alcohols and ethers. Now, an alcohol is an organic compound which contains a hydroxyl group, an OH. So, for example, we have our propanol 1 propanol or our propan 2-ol, and we can put the number at the front or in the middle. Now, the better way to put it is in the middle. And if there are multiple functional groups, we'll have to put it in the middle. Now, our alcohols can be classified as primary, secondary, or tertiary. And the classification is based on how many carbons the carbon that the hydroxyl group is bounded to is bounded to. So in a primary carbon, our hydroxyl group is bounded to a carbon that has only one carbon-to-carbon bond. So therefore, it's a primary. In our secondary, our alcohol is bonded to the main carbon chain to a carbon that is bonded to two other carbon atoms. So that makes it a secondary. In our tertiary, our hydroxyl group is bonded to a carbon bonded to three other carbons. Any type of type of alcohol that it is will be important when we talk about reactions later on. Now, when we name an alcohol, if it's the highest priority, it gets named in the suffix, and we drop the E and we add the suffix OL. If it is not the highest priority, then it gets named in the prefix. And we have to state the location always. If it's the highest priority, it gets priority in numbering. If it's not, then the higher priority thing gets priority. Okay, so when we name, we want to determine our compound, we want to determine our primary chain, we want to number it, and we want to go from there. So let's look at some examples.
So let's take a look at this compound and name it. So first we determine our carbon chain. 1, 2, 3, 4, 6, 7, 8. So we know that it's 8 carbons long. We have our longest chain. It can be bent. So we know my group is going to be oct. They're all single bonds, A and E. But we can see here we have a hydroxyl group. So that tells us that the E is going to be dropped for OL, but we have to state where it is. And so if I count from this end, it's on carbon 2. If I count from this end, it's carbon 7. So therefore, this would be an oct. And we drop the E. We have to state the location of the alcohol. So it's an octan 2-ol. Okay, so here we have what we would look for our longest chain. Okay, and as we're counting, we notice that we don't have one OH group, but we have 2. And so because of that, that means that even if this was not my longest chain, this becomes my root, because we want to put both of the functional groups in my longest chain. And so that means that this is a side chain, and this is a side chain, and they're both ethyls. My longest is 7 long, so it's hept, and they're all single bonds, so being heptane, but we're going to drop the E. And then we know that we have 2 alcohols, so if I count from this end, I'm on 2 and 7. If I count from this end, I'm on 1 and 6. 1 and 6 is smaller, so that's carbon 1. So therefore, these would be on carbon 3, both of them. So now when I go to name this, my alcohols are in suffix. These are prefix. So therefore, 3,3-diethyl hept in. Now I have 2 location to state. So it's 1, 6. And because it's 2 alcohols, it's diol. Now in this case, I have my alcohol but it's on the shorter chain. And so although I would want to call my 6-ring structure my root because it has more compounds, because the shorter one has the functional group, this becomes my root. And so therefore my root is going to be an ethane. I start off, but I'm going to drop the E because of that. And that means that this gets named as a side chain. So I have 1, 2, 3, 4, 5, 6. So that's a hex, and it's a ring. So that's a cyclohex. And because it's a side chain, it's a YL. So this is a cyclohexol. Right? This is an OL. This has higher priority. So therefore, that's carbon 1. So this is going to be a 1, and this is going to be a 2. So therefore, now when I go to put the name together, it's going to be 2 cyclohexyl ethane 1-ol. Now, when we go to draw the structure of them, what we want to do is we're going to follow the same process where we write out our root, we add any double or triple bonds, we add our functional group, and then we go back and we add our hydrogens. So here I have a 6-carbon chain, all single bonded together with a hydroxyl on carbon 3. So I'm going to go. So I have 1, 2, 3, 4, 5, 6. Then I'm going to go carbon 1, 2, 3. I'm going to add my OH. And then I have no double or triple bonds to add. And now I'm going to go back and add my hydrogens. So that carbon needs 3. This carbon needs 2. This carbon needs 1. This carbon needs 2. This carbon needs 2. And this carbon needs 3.
Okay, so some of the properties of alcohols, they have what's called a biting odor, so they have a strong smell. But more importantly, they have a hydroxyl group, which makes them polar. And also the hydroxyl group, because we have a hydrogen bonded to an oxygen, means that I can not only form London force, but I have dipole-dipole, and I can also have hydrogen bonding. So this has an impact on their boiling point and their solubility, because we would expect alcohols to be soluble in water as long as the carbon chain is not too long. And we would also expect them, because they have high attractions between themselves due to the ability to form London force, dipole-dipole, and hydrogen bonding, we would expect them to have a relatively high melting point. And now if we want to talk about melting point, we have to compare it to other things. And so what we often say is that it has a higher melting point than an alkane of an equivalent length. Okay? We know that we can form an alcohol through an addition reaction of a water to an alkene or an alkyne. When we do this, remember, just like we talked before, we have to keep in mind our Markovnikov's rule. 8. And so here's our example, just a quick example to remind you. A second method for forming an alcohol is if I react an acyl halide with a strong base. And what will happen is I can get a substitution where the hydroxyl group will replace the halogen. And so then I will get an alcohol formed this way as well. Now, another reaction that alcohols can undergo, or category reactions, is what we call a dehydration reaction. This is where we remove the water. And so the first one is that I could have an alcohol catalyzed by a strong acid, and what I can get is an alkene and water. And so one of the carbons will lose a hydrogen, one of the carbons and a hydroxyl group will also be lost. When we do this, we have to remember sort of the reverse of Markovnikov's rule and determining our possible products. Okay, a second dehydration reaction that they can undergo is if I have two alcohols reacting together. If I have two alcohols undergoing a reaction together, I can get the formation of what's called an ether. So here I have an ethanol reacting with a methanol, and I will get a formation of an ether plus water. Alcohols can also undergo a third dehydration reaction. This is where they react with another functional group called a carboxylic acid, and what we get is an ester and water, and the reaction sometimes is called an esterification. Now, another reaction that they can undergo, and we'll talk about this more later, is what we call an oxidation reaction. And if they undergo a controlled oxidation reaction, we can get an alkene, or if it's not controlled, we can go all the way to a carboxylic acid. Now, esters are a classification of organic compounds where I have two acyl groups connected to an oxygen. So here we have an example below where we have an oxygen and it's bonded to two carbon chains. Okay. And so when we name them, the longer chain is going to be my root, and the shorter chain is going to be named in prefix. Now, if one of the chains has other functional groups on it, or a double bond or triple bond, then regardless of length, for us, that group will be our root. Okay, ethers are slightly polar because they have a carbon to oxygen bond, but because they don't have a hydrogen bond to an oxygen, they cannot form hydrogen bonds amongst themselves. And so this affects their properties. So for example, since they can only have London force and weak dipole attractions, their melting points would be expected to be below that of an alcohol. Likewise, because they can only receive hydrogen bonds from water, they can't form, we would also expect their solubility to be less than that of an equivalently length alcohol. Now, reactions that form, the reactions that form our ethers, as we said, was a dehydration reaction between two alcohols. And then we can break up an ether by having it react with a halogen acid. So hydrochloric acid, bromic, hydroiodic, and it will give me an alcohol and an acyl halide. So we can see that here.